Okay, so today we'll cover small signal models for the diodes and the BJTs. Let's see. So we spoke about the common emitter amplifier. The common emitter amplifier, or any kind of amplifier, basically is a combination of AC and DC, right? So we're analyzing both the DC sources that are being applied as well as the AC input signal that needs to be amplified. The way we analyze these circuits is due to the method of superposition. Okay, so superposition, the principle of superposition applies for this analysis, meaning we can analyze the DC effect of the circuit separately from the AC. And then we can add up both of those together to have our combined final output. So we saw in the previous lecture how we can analyze the output of a common emitter amplifier using the load line method. Now we're going to go into a bit more of the details on the capacitors and then the small signal models. So in this circuit, we have these three capacitors that are connected to the base, the collector, and the emitter. And each one of them has a purpose. So if we are analyzing for DC, meaning we have applied only the DC bias, there is no AC input being applied to the circuit. Then we are fixing the Q point. We are fixing or setting the Q point with the applied DC voltages, right? And that's the purpose of the DC biasing voltages. So we do not want any other unwanted DC signal, any other noise signal to come in and shift our Q point away from our desired value. And the way to do that is by attaching a capacitor at the base terminal. So when you attach a capacitor, you're going to use the filtering properties of a capacitor. Okay, we're going to use the filtering properties of the capacitor. And what that does is it blocks any unwanted signals, any unwanted DC signals from reaching our base terminal. Because the steady state equivalent for a capacitor is an open circuit, meaning for DC, applied DC voltages, it's an open circuit. Inductors are short circuits. So this would block unwanted DC signal. So at the base, C1 presents infinite impedance to DC signals. At the same time, capacitors are going to permit the passage of AC signals, or we at least want them to pass AC signals, right? It blocks unwanted DC signals and permits passage of AC signals. So the values of these capacitors are chosen such that they provide very minimal resistance or opposition or impedance to the AC signals. So again, capacitor C1 is chosen with a value such that it's infinite impedance to DC signals and very low reactance or negligible reactance to AC signals. That is the purpose of C1. C2 is also exactly the same. We connect it at the output so that our desired AC signal is amplified and is available to go on to the next circuit or to the load. But we do not want the DC component to come in there. If you'll recollect from the lab output, the AC output was amplified, but it also had a very large DC component in there. And we attach a capacitor at the output to block that large DC component. And that's the purpose of C2. So C1 is connected to the input side, and the output side, we connect C2 for the same purpose. Okay. Then in addition to those two, we have a capacitor C3. Okay. Capacitor C3. Function or the operation is exactly the same, but the function and the application is a little bit opposite. It blocks the DC and it allows AC to go through. So again, the operation and the functioning is the same. The C3 blocks DC, meaning it keeps any unwanted DC signal from affecting our bias point from the emitter terminal. So again, blocks DC from affecting the bias point or the Q point. And if there are any other unwanted AC signals coming through the emitter, they will not affect the bias point because they are being bypassed straight to ground. Okay. It provides a pathway for AC signals to ground. So the names of these capacitors comes from their application. C1 and C2 basically couple the AC signal either as input into the amplifier or as output to the load. Since they are coupling the AC, they are known as coupling capacitors. So C1 and C2 are known as coupling capacitors. And C3, as the name suggests, it bypasses the AC signal, provides it a pathway to ground. Hence, it is known as a bypass capacitor. Okay. So again, we are using the filtering function of a capacitor. And depending on the application, we call them either a coupling or a bypass capacitor. Okay. So the addition of these capacitors allows us to separate the analysis. We can now analyze the DC separately and we can analyze the AC separately. So then let's take a look at how the circuit looks for both the DC and AC input signals. So for DC analysis, all we do is we replace all capacitors in the circuit and all inductors in the circuit with their steady state equivalent. Steady state means you're applying DC voltages, DC inputs, and they have reached full charge. They've reached full charge. So okay. Capacitors replaced with an open circuit, inductors replaced with a short circuit. Okay, with DC steady state equivalents. Just to make it more clear, DC steady state equivalents. And when we do that, we can see this section is cut off. This section is cut off, as well as the emitter resistor RE. Nope, sorry, that's not AC. This is DC. So the input and the output resistor and the input voltage is cut off. And the only thing that remains in there is your VCC and the 4 resistors. So now you have a 4 resistor bias or a voltage divider bias circuit. So results in a voltage divider bias circuit. Okay, voltage divider bias circuit. And so now we have separated out the AC from the DC, and we simply analyze the DC voltage sources, which is VCC. Now, again, impedance, I mean, the capacitor values are chosen such that the impedance is very high for DC and very low for AC. Otherwise, this would not work. Make sense? Okay. All right, let's take a look at the AC side of things. So for AC analysis, what we do is replace all capacitors and all inductors with your AC equivalents. Meaning capacitors are now replaced with a short circuit, inductors replaced with an open circuit. All sources and DC sources are also replaced. Voltage sources are replaced with a short circuit. And current sources are replaced with an open circuit. Okay, short circuits and open circuits. Okay, so if we take a look at a circuit example, what do we see? Capacitors are shorted out. So AC input signal has a direct pathway into the base. Output can go directly to the load resistor. Now RE is canceled out because capacitor is a short circuit. And then the voltage source plus VCC is shorted out. So it's connected to ground, 0 volts. And what that does is it brings RC in parallel with RL, or the load resistor, because both of them are connected to ground. And hence RC in parallel with your output load resistor. In this case, the notation is R3. At the same time, R2 is also brought in parallel with the other base resistor, R1. And so the circuit becomes like this. You have R1 in parallel with R2, and then your collector resistor is now in parallel with the output resistor. You can reduce the circuit as much as possible. In this case, R1 and R2 are in parallel, so we can replace them with its parallel equivalent. And same thing with RC and R3. And at this point, we choose a BJT small signal model that fits our application. and then we obtain this circuit. So you're applying a small AC input signal, and then we can analyze the circuit using any small signal model that fits our application. And that's going to be the next couple of slides. So far, so good. Okay. All right. So then let's look at first the diode and then the BJT. What exactly is a small signal model and how small does it have to be? Right? We keep saying small signal. And as a reminder, the purpose of using small signal models is so that we can treat a small region of the characteristics as linear, and we can apply all our linear analysis techniques. Okay, all the linear analysis techniques. So first up is the small signal analysis or small signal model for a diode. Okay, now in the diode, it's a far simpler model because we only have two quantities, VD, the diode voltage, and then ID, diode current, right? For the application of a DC input, we have VD and ID, and that would be a Q point. That Q point, of course, comes from the external circuit, the external applied voltage. And so the Q point is fixed. Now, if you apply an AC input on top of the DC, our Q point is going to shift away. And that shift is represented by this lowercase id and lowercase vd. So id and vd are the shifts away from our DC bias point or from the Q point. Okay, from the Q point. Now, these deviations must be small enough. Again, keyword is small signal analysis or small signal model. So their shifts must be small enough so that we can treat it as linear. And if we can treat it as linear, we can first write out diode resistance from Ohm's law. And that would be VD over ID, the shift away. If we take the inverse of this diode resistance, that gives us the conductance GD. And that graphically is the slope of the characteristics. The small linear portion. Okay, that's the slope of the characteristics. So diode conductance, diode resistance is RD. And then the inverse of that is, of course, conductance GD. Okay, and GD is given by the slope of the curve. So directly ID over VD, or delta ID or delta VD. Now, to find a value for GD, we can insert the diode equation into the resistance equation. And then we reduce that, we obtain GD as ID plus IS over the thermal voltage VT. This is for a forward bias diode. Okay, forward bias diode, and we plug in the diode equation. Now, in a forward bias diode, ID is going to be typically much, much larger than the saturation current IS. And so we can approximately write diode conductance GD is equal to ID over VT. So in the forward bias, it would be the diode current ID over VT. And then we can say that the small signal model for a diode can simply be represented by a resistance RD, the voltage VD, and current ID flowing through it. If that's a small signal model, what is the value of the voltage or deviation from the Q point that can be considered small enough so we can actually use this model? And that turns out to be must be far, far less than twice the thermal voltage, which at room temperature is approximately 25.8 millivolts, or if we stick with our book, then 25 millivolts. So approximately 50 millivolts. So diode voltage must be far less than 50 millivolts. If we take a ratio of 1:10, we can approximately write that the shift for the diode must be approximately equal to 5 millivolts to be considered small signal and to be considered linear. Okay, to be considered small enough for linearity, the diode voltage from the applied AC must be less than 5 millivolts. Okay, these are also all part of the homework that is due next week. Good. All right, then let's look at the BJT model. Okay, BJT model. Actually, this is not the hybrid pi. This I have to change that out. It's just a BJT model that we are starting with. We are treating it as a two-port network. If you recall from EE 212, final chapter. And we are separating out the input side and the output side. This is a Y parameter two-port network. Okay, Y parameter two-port network. So we have the input side on the left, and too close. Let's bring it away. Input side, output side. For a BJT, the input is the base, output's usually taken across the collector. And so on the input side, we have the base current and the base voltage. base voltage, of course, is VBE. So as the input, we have IB and VBE, and at the output, collector current and the collector voltage. If you notice, both currents are going in, okay? And because that's acting like a current source and a current sink. And so the normal accepted convention is always that both currents are flowing in. The collector current from the output is also flowing into the BJT. And then, of course, IB and IC combine to form the emitter current, IE. So if we write the equation for these two sides, we can write IB and IC as equal to this. So IB, the base current, is G pi times VBE plus G mu times VCE, the input voltage and a combination of the output voltage. And IC, the collector current, again, summation of the input voltage and the output voltage. Now, what do we see? IB just a second. Okay, so what do we see here? IB is equal to VBE and VCE. IC is equal to VBE and VCE. If VCE is equal to 0, we can write IB and IC simply as G pi VBE and GM VBE. So if VCE is equal to 0, and that's what we would expect at the Q point. If VCE is equal to 0, then G pi conductance on the input side is IB or VBE. This is, of course, at Q point. And similarly, then GM is IC or VBE. What do these two terms mean? They are both from the input side, but one of them is the ratio of the input current and the input voltage. The other one is the output current and the output voltage. The first one is showing you the input conductance. The other one is the transconductance. How is the input being transferred to the output? Okay, so transconductance. GM, again, is an important parameter. Okay. And for the second part of the equation, if VBE is equal to 0, then we can write G mu as IB, input current or output voltage. And we can write GO, output conductance, as IC or VCE. This is on the output side. Okay, output side. And of course, the reciprocals of these conductances also gives us the resistance, the input resistance and the output resistance. Okay. So now at the Q point, what are the values of these quantities? So at Q point, G mu is going to be 0. G mu is going to be 0. Gm is going to be IC over VT. G pi, let me write it here, is IC. Oh, sorry, not G pi, GO. Let's do GO first. GO is IC over VA plus VCE. Early voltage plus the output VCE. And then G pi can be written as IC over beta O times VT. And beta O is a new term we defined to simplify the equation for G pi. So beta O is the forward beta, beta F, and then denominator is 1 minus IC times 1 over beta F times the partial derivative of the forward gain to the collector current IC. And this is at the Q point. Right? Beta F is the forward current gain. Beta O is the small signal common emitter current gain. Okay. So this is the, let me write it here. Small signal common emitter current gain. Okay. And from here, we can simplify this model to get one of the most popular models, which is the hybrid pi model. It was called the pi because, well, somebody early on thought it looked like the shape of a pie, the symbol pi, hence known as the pi model. And this is the hybrid pi model where we simplify it, and we simply have the input resistance R pi, output resistance RO, and we can model the output side as a dependent current source, Gm times VBE. Gm times VBE. And for the hybrid pi model, the equations are Gm is equal to IC over VT. This is the transconductance. R pi is beta O times VT over IC. That's the input resistance. And then we have RO, which of course is 1 over GO. And that would be VA plus VCE over IC. That's the output resistance. This can be further simplified as simply VA over IC. And that's it. That's our hybrid pi model. And that's all you would need for the homework problems. When we come back from the break, we'll look at an example of how we can use these models and analyze a circuit or an amplifier circuit, BJT or an amplifier circuit. And we'll have one final quiz. Not this Monday. Monday after that. Yeah, following Monday. One final quiz before the final exam. Okay, so we'll end class right here today. As I said, slightly smaller, not as small as I expected, but slightly smaller. All right, have a happy Thanksgiving, and I will see you all in next month. I will be available all through the week, all through the break. So if you want to send me an email, want to meet up on the Zoom, feel free to reach out. Okay. Homework, I made it due. I was gonna make it due on like Monday, but then I said, let's extend it by one day. So I made it due Tuesday. But you want to get it done as soon as possible, you can get it done as soon as possible. And the rest of the week, don't have to worry about too much. So you can enjoy your Thanksgiving break. All right.